everybody. Today we'll have Niv Haim, which is a PhD student at Weizmann, presenting his work. Niv, please.
Hi, hi everybody. Thanks for the invitation. Eran, I think I hear some noises from someone in the audience. Okay. So hi everybody. I'm Niv Haim. I'm a PhD student, like Eran said, in Weizmann Institute. I'm advised by Michal Irani. And today we'll talk about reconstructing training data from training neural networks, which is the work that we presented in NeurIPS a few weeks ago as an oral presentation. It is the joint work with Gal Vardi and Gilad Yehudai, who are first equal contributors, and Ohad Shamir and Michal Irani. So the motivating question in our work is, can the train set be recovered from a trained neural network? And what I mean by that is, if you are given a trained neural network classifier, in this case, a binary classifier, and say it was trained to separate between two sets of images, the images of vehicles and the images of animals, in this case, from the dataset of CIFAR 10. If I give you this trained model, can you retrieve somehow the training set, or samples from the training set, or something from the training set? And this is what we show actually in our work, that for some cases, this can be done. And here you see some examples of reconstructed samples from the training set of this model. So can you see, by the way, Eran, can you see my pointer?
Yes, we can.
Okay, great. So as you can see, these samples are reconstructed, and they can clearly tell that, clearly see that these are images from the training set, but just by comparing it visually. So you see that this is the same car, and this is the same airplane. And of course, there is some noise going on, but definitely, I mean, some examples were clearly reconstructed from this model. Okay, so how do we do that in general? We define some loss over this trained model, and we're going to minimize this loss with respect to the input. So the only optimization variable in our method is going to be the input, which we don't know. We don't know x's after we only have the parameters and the architecture of the model. And we want to solve this optimization problem with respect to some loss. So we will just sample some inputs at random. So this is how it looks. And then we are going to optimize this loss. We're going to tweak, to change these x's in order to minimize this loss. And this is how it looks like. And slowly, these x's will converge to samples from the training set. Now, the nice thing about our work is that this loss that I'm going to tell you later is motivated or actually derived from a deep theoretical understanding of what happens to the parameters of the model when you train them with gradient descent. And in general, these theoretical results, what they say is, when you train your parameters, you start from some theta, you train your model, you change the parameters in order to minimize the classification loss, and you do it with gradient descent. The parameters will converge to a very specific solution, theta star, that we can actually specify with a set of equations. So if you believe the theory, and you believe that the model that you trained converged to this very specific theta star, that we can specify this a set of equations. So f is known, and x is going to be the training samples. So we have something that relates the parameters of the trained model to the training samples. Now, once we are giving this model, we have the trained parameters, we don't have x. So what we are going to do is just change this x in order to satisfy this set of equations. This is the overview of our work. And of course, I have to tell you about the details. What is this loss, how it is derived. But first, let's have a look about how it is related. Let's get some intuition from from practical results of visualizations of deep neural networks, and how it is related to privacy, of course. let's start with visualization. So there are many visualization techniques out there. And the reason I'm showing it is because this method of changing the input with respect to sum loss is very familiar in this visualization techniques. So if you did some introductory course in deep learning, for example, even the CS231N by Stanford, there's a specific lecture about visualization techniques. And most of them are doing the same technique. So they define some loss. And what they are interested in is what can we find inside these parameters of the model? What lies inside there of the parameters, what lies in the representations? And the method is very similar to what we do. For example, this seminal work by Mahendra and Vidali from 2016, they were the first to show what happens in convolutional neural networks. And what they do is they take this random input and they want to change this input as we do in order to see if they try to maximize some score. So for example, if they try to maximize the label of the frog and change the input in order to see what label, what input would maximize this frog score. So that's what they're gonna see. That's something start popping on this image. You see this kind of eyes of the frogs, or if you do it with black swan, you see this beak or a cheeseburger here. You see that. So the image is going to change in order to maximize something. So you can look at it as some kind of, again, like maximizing or minimizing some loss, which is going to be just a score of some class. And this is called as visualization via activation maximization. This was also done for the sake of artistic results. So also another very famous work, Deep Dream by Mordvintsev, are doing basically very similar things, but instead of starting from a random input, they start from a noun given input. So you have here the Mona Lisa, and then you start changing the Mona Lisa in order to maximize some scores for a pre-trained classifier. And you see some stuff start popping out with like eyes of a dog, or if you do the same with the Starry Night by Van Gogh, you see that some donkeys come out or cars. So this gives us some intuition that these methods actually reveal some secrets about the training data. So we have this pre-trained model. If we were not told what this model actually learned, and we just want to start changing the input in order to maximize some labels, we'll see that these donkeys pop out or a car, and it tells us that, well, basically there were some donkeys in the inputs, or there were some cars in the inputs, or dogs, definitely. This was also taken to very nice results if you include some prior, some GAN prior. So if you do the same activation maximization, but now instead of just changing the input, you change the output of some pre-trained GAN on the same distribution, so you can get much better results. So here is training images of ImageNet, and these are images that were synthesized from this trained classifier by using some strong prior on the data. So we don't know the exact data. We know that this classifier was trained with images from ImageNet, so we can train again generative adversarial network on images from ImageNet, and then use it as a prior in order to do this activation maximization, and you get very nice images that resemble the training data. But the question is, can we recover exact training samples? Again, I'm hearing some noise from someone, so if you can mute yourself if you don't want to ask anything. Okay, right. So it is not surprising that by doing this method, we see something that is related to the training set, but can we recover exact training samples? So this brings us to the privacy section. And let's see some related privacy attacks to our method, because you can think of our method as an attack, because you retrieve samples from the training set. It might be harmful, especially if you work in, for example, a good example would be in the health sector, where the data privacy is very important. You don't want the data to be leaked to unknown people. So I think the go-to method, the go-to approach nowadays is when machine learners in the health community get some data, so they say, I'm overly generalized here, of course, but they say, okay, I'm not going to publish the data, but so give me your training data it would be like for some hospital, give me your training data, images of some ultrasound or röntgen. I will train a model on this data, and I will only publish the trained model. And there will be no way of getting the training samples from this model, right? But then, okay, this is part of what we show, that only from the trained model, only from the parameters, you can in fact get some samples. And of course, it works only for several cases, but this is very related to privacy issues in machine learning. And some other methods that are related would be this technique of doing, like we saw, activation maximization for the sake of visual understanding or artistic generative images. The same approach can be used to try and retrieve samples from the training set. So we saw that you can get this donkey or the car. So there is a nice line of works that show that using this method, you could retrieve something which is related to your training sample, but it is fairly limited setup. So for example, in the seminal work in the field by Fredrickson, what they show is they train a classifier to classify faces. So they have about 40 faces that they want to detect in images, but each face is going to be a class, but they only have about 7 images per face. And if you have this setup and you do this activation maximization, you take your trained classifier, and where for each class you have a handful of images, by activation maximization, you will get something that looks like this image on the left here. So this is what you get from doing this model inversion, activation maximization. And this is a real image for that class. So you will get something that looks similar, but it is kind of getting you the average of the class. So this is limited, because if you have many samples per class, getting the average would not be so meaningful. But this is one way to look at it. Another interesting work in terms of privacy would be membership inference attacks. And what this means is I have a pre-trained classifier, and I want to ask whether a specific sample was used in the training set of this classifier. So, I mean, why would it be interesting? For example, again, if we go to the health industry, and I want to classify, say, for some images, if there is a tumor there or not. So, and I trained my model on certain images. Of course, some of them had a tumor or some of them did not. But then I bring the image of someone that I know or my own, and I check it. So, and then the membership inference will tell me if this image was in the training set or not. This is already good information about giving already a good prior if this person has this health issue or not. So this is why it is interesting. But for these attacks, you need knowledge of specific training samples. So in order to do membership inference, you need to give me a sample from the training set, which is something that we don't want to do in our method. And just another interesting thing, which is related to the big hype of large language models. So there were also some nice works trying to reconstruct data from large generative language models, for example, by Carlin et al. So what they show, they take this huge language model, and by finding very specific prefixes or some prompts, like you have here, so you say is whatever something something, and the model would generate some data which might be sensitive, like telephone numbers or addresses that you wouldn't want any users to find. So this is also kind of sort of reconstructing data from the training set of the image, but it is very tailored to language models and generative language models. So this is kind of the landscape of privacy attacks in machine learning related to our work. Okay, so we've briefly discussed about visualization techniques and privacy and how it is related. So let me rephrase our contribution in our work. We show in our work that we reconstruct large portions of actual training samples from a trained binary MLP classifier. So in our work, we focus on MLPs, which is a kind of neural network, but fairly simple one. So it's relatively small scale, but still it is the first time that that reconstructing large portions of training samples is being shown, even for these relatively small scale networks. And we have no additional information about the training data. We don't want to use any information. Now, what is left here is to understand the method. And as I promised you, our loss is motivated by theoretical results, specifically the theory of implicit bias of gradient descent. And let's now move into the theory part. So I'm going to tell you about this theory of implicit bias and its results, and then show you how we use it in order to build our loss. Okay, so what is the implicit bias of gradient descent? What exactly is this, where it comes from? And it all starts from a question or empirically seeing that deep neural networks, you train them on some data set, and you can fit the data, you can fit your training data, you can get zero training error with basically infinite number of solutions that can fit your training data. But for some reason, deep neural networks fit the data, but also generalize very well to unseen data. And this has puzzled theoreticians. Why deep neural networks converges to these solutions that also generalize very well? The main result in this field is a theorem by Sudri et al. From a few years ago. And what they show is that if you take logistic regression and you train it with gradient descent, the model, which is a linear model in the case of logistic regression, will converge to the hard SVM solution. Okay, so what I mean by that, you have your data, which is linearly separable in the case of logistic regression. And there are many solutions to classify these sets of data points. You have the green one, the blue one, the black one. You have many solutions. If you want to train it with hard SVM, you will get the classifier that would maximize the margin, the black one here. But in order to train something with SVM, so training SVM, you explicitly require your optimization problem to seek for this largest margin solution. Doing logistic regression has nothing to do with margin or maximizing the margin. So let me rephrase why this theorem is so interesting. So you have your model, you have your data. You want to train a linear classifier, and you are going to do it with logistic regression, which is basically you define this loss, which is maximizing the likelihood of your model with respect to the data. Then you want to change the parameters, you want to change your linear model in order to maximize this loss. And when you solve it with gradient descent, it will converge to the same solution of hard SVM without any requirement on the margin. Then why is it interesting in another sense? Because SVMs, if you remember or you learned about learning theories, so SVM solution generalize better than just any linear model. So this theorem gives us a hint of why training, you can look at deep like neural networks. So linear model is a very simple neural network, but nevertheless, it is a neural network trained with logistic regression loss, which is very similar to the cross entropy loss for multiclass. Trained with gradient descent, you converge to a very specific solution that now has these two properties. It generalizes very well, and you can specify it using some equations. Okay, so this property of gradient descent is called the implicit bias of gradient descent because this is implicitly converging to a very specific solution. And this was later generalized, this theorem was generalized to deeper neural networks by these fellows here, right? So what they say, without going into all the, of course, there are many details, but without going into all the details, they say that deep neural networks trained with gradient descent will converge to the now rephrase it a bit more formally so we can get to the loss part. You have your trained classifier phi, and this trained classifier, you train it with gradient descent. It is a binary classifier. It will converge to some solution which is specified by this set of equations. So don't be too afraid of this set of equations. I will also explain it a bit more carefully later. But what I want you to see here, that this solution that the model converged to, which is relating the parameters of the model to the inputs, is that you have this set of equations that can relate the parameters and the data. Now goes our key observation in our work. If you train your model, while training your model, the data is fixed, and the parameters of the model will converge to this solution. Now, what we want to do, we want to do the opposite. So for reconstructing, now we get a trained classifier. Theta is going to be fixed. Now let's just solve this set of equations for x. Question so far? Again, I can't see the faces. I can't see any of you. So if you have any questions so far?
Equation number 1 represent what? Sorry?
Okay, so I didn't tell you how I got to these equations. I just told you that training this model phi with parameters theta, if you train it with gradient descent to classify your data, it will converge to something. It will converge to a very specific solution. And this solution can be specified by this set of equations. So, for example, here we have M solution. Okay, sorry, maybe I didn't tell you what it means. So for each scalar parameter in your model, we have, say, 1 million of them. M is 1 million. So for each scalar parameters, you will have this. You have 1 million equations which relate each parameter of my model to my model phi of theta and x. It has some derivative here. It has the label, and it has this funny thing lambda that at the moment you don't understand. So is it okay? Tell me again, I can't see you. So
yeah, it's okay.
Okay, it's okay. Okay, great. Thanks. So you have these equations, you have some other equations, but the most important thing is that you can write down these equations and that your model, while training it with gradient descent, converge to this solution that you can write down the set of equations that describe this solution. Okay. So now if you believe the theorem, if you believe that the model converged to this solution, what we do is we specify the following losses. So the first loss, L theta, is just going to be the same as the first equation, just going to say, let's just let's find x's that minimize these equations. It's basically just if you want the left-hand power to be 0, let's just find the x's that make the norm of it as small as possible. So this is going to be the first and most important loss that we are going to use. You see, it is fairly complex. It has these derivatives. It has also this lambda. It has all sorts of things. But if we believe that our model converged to this solution, if the thetas, the parameters of the model converge to this solution, then we can just find the x's, because now we have the parameters. We want to find the x's, the input x's, that would satisfy this equation, or that would just minimize this loss. We also have another loss, which is related to the lambda, to the third equation, that requires all these lambdas to be positive. So we just want these lambdas to be positive. And we require each pixel in the optimization. We have this prior, and I promised you that we are not going to use any information about the data set. So we only use a very simple requirement that the image would be bounded between -1 and 1. Also, it's like the most simplest form of prior that you can use on your data. Okay, so now we can look at the algorithm of our work. The input is going to be a trained classifier, binary classifier phi, with parameters theta, and that acts on some x's. We want to find these x's that were used in the training set. The optimization variables are going to be xi, of course, the inputs, and this lambda I, which is going to be a scalar for each x. So we added another optimization variable, lambda I. We don't know them, so we just initialize them at random. We have the yi's, the labels, that are going to be either -1 or 1. We set them to be in a balanced manner. So we just say we want to find 1,000 x's, which belong to 500 belong to the positive and 500 to the negative. I can talk about it offline. It's not the most important thing, but you can show that it is enough. It's good enough to do it this way, to be in a balanced manner. And once we initialized our parameters, we just optimize them to minimize the loss, like I showed in the beginning. So we have these 3 losses with some weights. So it's going to be like 1 or 5, something that we played a little bit with it. But we have this loss. And again, as you've seen, this is how it looks like. You have these x's sampled at random in the beginning because we know nothing about them. And just by minimizing this loss, the random x's would drift slowly into samples from the training set. Okay, so before I go to the next section, so here's another good point to stop and ask if you have some questions, because what I'm going to do next is I'm going to tell you a little bit how we got to this set of equations. Any question about the method or something wasn't?
Yeah, maybe before how you get them.
Yeah.
How do you optimize on the El Prior, on the bounding of the X?
What is related the loss? So we put some kind of like a value. So if for each pixel, if you go outside this bound of -1 and 1, just give, so between -1 and 1, it's going to be 0, and outside it's like linearly going like some value. It's basically like this game of 2 values that you can think of.
Okay.
Just this is like a simpler way to look at it than now writing the 2 values here, I thought. Yeah.
You have some information about the number of training samples or something?
Okay,
like
that's a great question. Basically, you don't. If you look at it as a sort of like an attack, you don't know the number of samples. In our experiments, So we've played with training sets of size 500, 1000, so say 1000 at most. And we checked this. So when you come and you want to reconstruct, you have to define, say, this n here. You have to define how many samples are you going to reconstruct, and they should be, in general, at least as the number of samples in the training set. Not really, but this is like naively thinking of it, and we don't know it. And so actually, you can it cannot be 1 or 2 or 3. It has to be a lot. What we show in our experiments is that we take normally twice the number of training samples that we used in the training part. So if we train the model on 1,000 samples, we reconstruct 2,000 of them, and most of them will become kind of like garbage, and some of them will converge to samples. And in general, we don't know. We did try to play with changing n, and it is kind of robust to some extent. So it doesn't have to be twice. It could be like the same or even a bit less. And in general, this is still like a relatively open question, but it is very important to know this thing of how many initializations you use. So yeah, I mean, we tried with some options, and it's relatively robust, but in general, it's a good question for future work, I would say.
Thanks.
Yeah.
And do you have a way to distinguish between the garbage and the? How do you know if the training sample is
Okay, right.
from the training set?
So it's a good question. So I'll get to it in the experimental section. It's a very good question, yes, because just to rephrase your question, just knowing whether reconstruction is a good, how do you know that a reconstruction is a good reconstruction? It is a complex question in itself, unrelated, not only in our work, but is general. So, but I'll show you the heuristics that we've used to do it later. Okay, so let's briefly explain this set of equations that I told you. So if you remember these equations, so you train your model, you have the parameters, they will converge to a very specific solution that you can then specify by this set of equations. Now, where these equations come from, and this is going to be very similar to the theory of SVMs. So if you are familiar with SVMs, what I'm going to show you is not going to make anything new for you. So you can either like be happy that you're listening to something that you already know, or you can go to Twitter. But it's going to be very, very simple, similar to that. Okay, so I'm going to tell you about solving maximum margin problem, because we saw that the theorem tells us that the parameters converges to the solution of a maximum margin problem. Then what is a maximum margin problem? So you have the classifier phi with parameters theta and x, and it is the binary classifier. In our case, it can be generalized to multiclass, but we're gonna. So it's if you want, we can take it offline and talk about multiclass, but so just saying that it is possible. But we are going to focus on binary classifiers here. And you have the training samples, xi and yi. You have n of them. And by solving maximum margin classifier, as you do with SVM, you are actually solving, you define this optimization problem. What is this optimization problem? This is a reminder of SVM. So you have your data, and you want to find the linear classifier with the maximum margin. Usually with SVMs, you use a linear model. Any linear model can be represented by some vector, theta. And the equations are going to be just that. What do we have here? We have this minimization objective, which is basically related to the margin. So by minimizing this norm of the vector, you actually maximize the margin. This is not trivially to look at it, but any introduction to SVM shows you how to like geometrically relate this vector to the geometrical margin. You can do it, and then you get that by minimize this thing, you can actually maximize the margin. And then you have the constraints. the constraints are what? Such that for each sample in the training set, for each xi, you need this thing to be larger or equal than 1. What does it tell us? So thinking about it, this is going to be, if it's correctly classified, then for each x, theta times x is going to be either plus or minus, depends on the class, times yi just tells us that this thing is going to be, if it's positive, it means that it's correctly classified. So you're looking for the predictor with the maximum margin such that all the training samples are correctly classified, larger than 0, but actually larger than 1, larger than some margin. Okay, so this is like brief reminder. One done. Now, when you have a deeper model of some classifier phi, then these equations, this optimization problem is just going to change and be any phi of theta x. So this is the optimization problem that we are trying to solve. And how do you solve constrained optimization problems? If you remember from calculus 1, or actually let's do it even before, right? If you would not have any constraints, you could just take the derivative with respect to your variable equal to 0 and then solve. Now, when you have constraints, if you remember, if it was equal constraints, you could have used the Lagrange multipliers. So you're going to solve theta with using the Lagrange multipliers. You write down the Lagrangian, which is this thing, and then you're going to derivate it with respect to theta, derivate with respect to lambda, and equal to 0, and then solve this. But what we have here, we don't have equality, we have inequality. So we cannot use this simple Lagrange multipliers. We will have to use something else. And this is called the generalized Lagrange multipliers, or KKT conditions. And if you write these sets of conditions for solving this optimization problem, you will get the exact equations that we've seen. So to rephrase what we've just seen is that these sets of equations that is going to specify the solution that we're going to converge to is basically the KKT conditions for the maximum margin problem. And that's why you have this lambda pops up, because this is kind of the Lagrange multiplier. So you have these equations that relate the theta, the parameters, to the training data xi, yi, plus this annoying or lovely lambda Lagrange multiplier, which is just a scalar per data sample. Now, back to the theorem that I told you about before. So the theorem says that any deep neural network, with some assumptions, of course, that but in general it would work for a very large set of neural networks, in descent on this dataset will converge to a solution of this. Exercise to do. Let's just count the number of equations that we have, because what we are actually trying to do is kind of invert a system of equations. And the most important equations here are those under number 1. So we have m equations, which m is the number of parameters in the network, number of parameter scalars in the networks. We have m equations. And how many unknowns do we have? We have the xi's and the lambda i's. Xi is going to be of some dimension d. Lambda is a scalar, and we have n of them. So we're going to have this amount of unknowns. And if we assume that our model is over-parameterized, if we have enough parameters, then we will get this kind of over-constrained system of equations. And it will be good intuition of why we will be able to solve this system of equations. So this is a good assumption to have, because like empirically, people normally use over-parameterized networks. It's easier to train. And in our case, it will make sense, because then you can reconstruct the data. Whoops. Yeah. Okay. Sorry, something gone wrong with my presentation. I'm sorry for that. Okay, so we're done with the math here. So we've talked about visualization, we talked about privacy, we've seen the theory. So I hope you get the sense of where we get this loss that we use. And now I want to show you some experimental results. So let's take this 3-layer MLP model, fully connected. So by MLP, I mean fully connected layer, ReLU, fully connected layer, ReLU, etc. And I'm going to train it as a binary classifier using 500 images, 250 images per class. And we're going to train it on binary CFAR10. So the images are going to be from CFAR10, vehicles versus animals, or binary MNIST, which is just odd versus even. Both models receive quite high generalization accuracy, so 80% accuracy, which is far from the random 50%. And this is how it looks like after we finished reconstructing the images. So I show you the best reconstructed images. So I still have to answer your previous question. But if you look at the best reconstructions, this is what you get. And if you compare them to images from the training set, you see that they are fairly similar, at least like the best ones in some metrics that I will tell you in a bit. And then you get less and less good ones. And so at some point, it's hard to tell whether this is a good reconstruction or not. Yes, you can maybe guess or not. Is it a good reconstruction of 2 or not? And it's a good question. But at least there are, say, 20, 30 images that were reconstructed to good visual quality, and the same for CFAR, for the CFAR10 images. If you compare them to the train set images from the training set, you see that these are good reconstructions. It's not some random stuff. It is not like something that looks like the images. It is actual training samples. Okay, so we show these methods on relatively small scale models, so on MLPs. And the question is, maybe for these very simple models, you could actually retrieve these samples in a much simpler way, right? Because our setup is relatively simple, right? It is 3, 4, 5 layers MLP. It is only 1,000 images. Maybe you don't need all this complex loss system in order to get something similar. Maybe you can find it otherwise. So do you have any ideas? Actually, the answer is already written, but any ideas on how you can find it otherwise? Okay, again, I don't see your faces, so I don't know if you're all asleep or not. Anyway, so we can do something like activation maximization. If you remember, we have the classifier. We can just tweak, we can change the input to the classifier in order to maximize or minimize the output. So, for example, let's see how it looks on a very simple learning problem, 2D problem. So the inputs are now in 2D. Here we have 20 samples in our training set. All these X's, blue and red X's. The red X's correspond to the positive class, blue correspond to the negative class. And I trained a deep linear network on this training set. So now the model gets 2D pointers input, and it outputs just a scalar. If it's positive, then it's belong to the positive class. Negative would belong to the negative class. And you see that the model manage to fit the data well. So red is positive, blue is negative, and all the training samples are correctly classified. Now let's try to do activation maximization. I sampled many points, and then I want to change these points in order to either maximize or minimize the output of the model, the label. So it's basically what's going to happen is it's going to go to a local extrema, either minimum or maximum. And by doing so, we get all this local extrema that means nothing, but you see that also some of the training samples are located on a local extrema. So out of 20 training samples, 7 of them were managed to retrieve but just by activation maximization. Now let's try to do the same with our loss. The same model, I initialize some sample as at random, and then I start minimizing my loss, changing the axis in order to minimize the loss. And you see that at some point they will converge, and basically all the training samples were reconstructed. So 20 out of 20 were reconstructed in this very simple example. So at least in 2D, it's a little better than activation maximization. Let's see what happens in like a more realistic scenario with images. So if I try to do the same with images, I have this binary classifier trained on CIFAR10 images or MNIST images, and I'm going to look for this local extrema for this model. Then this is what I'm going to get. I'm going to get either very strange local extrema, negative or positive. I'm going to get the average class, which is similar to what we've seen with the model inversion with faces. This is very typical result with activation maximization. But I didn't get anything that looks something like the training set samples. So this is using activation maximization could not retrieve the samples like we get using our loss. Any other idea? Maybe you can find it in another way. I give you a hint. We are using MLPs. The first layer of MLP, so the first fully connected layer, basically looks at each input, even if it's an image, it looks at it as kind of a vector, and then it multiplies this vector by some matrix to get the first hidden state. So the first layer in an MLP, the first fully connected layer is basically just a matrix where each row is in the same dimension of the input dimension.
So you can do the reverse, like the inverse matrix.
Yeah, so or maybe the model just learned to nicely put all the training samples inside this matrix of the first layer. Because if we have, say, 1,000 images in the training samples, and we have the first layer takes us from dimension D to dimension 1,000. So what we have is just 1,000 vectors in the first matrix. So you can just look at this first layer and see if you can find something there. So this is how it looks like. This is how the weights of the first fully connected layer looks like. So on the first row, these are vectors, so rows from the first fully connected layer reshaped to the shape of an image. And you see that it did do something which is kind of similar to what I told you. So for example, this airplane, you can find it just by looking on the first fully connected layer. So you can find this airplane, or you can find this bird, or maybe this ship, but then that's pretty much it. So you could reconstruct some of the images. So say 3 or 4, or for MNIST, you get this 8 and 9, but then, I don't know, it doesn't mean anything, I think. But definitely not 20, 30, 40 like we showed. So it's true that we show our method for relatively simple cases, but nonetheless, there is no better way of reconstructing these training samples by any method that I'm aware of. Of course, if you can think of anything, please tell me. But these are kind of the baselines that we've seen, that we thought about. So I want to end.
Can I ask a question?
Yeah.
So you have a very strong argument here. You say that the first layer weights encode the training data in its own weight, like
for our simple setup. So for MLPs with not a lot of training samples.
Yeah, when we have like too much samples and in the first layer doesn't have enough weights to encode all the training.
Exactly. That's what I guess would happen. Yes. So you will not find it there.
So it's really.
Yes. But our work is at the moment empirically is limited for this kind of MLPs. Of course, we are working to make it more realistic, but we've only managed to show this for MLPs. But what I'm saying is, even for these small scale models, you can think of a better way of finding these training samples in the parameters of the model. So you can find maybe 3 or 4 of them in the best scenario, but not 20, 30, 40 like we've showed.
Yeah.
Okay. So I want to end the last part is a nice analysis of showing the relation of our empirical evidence to the theory. And then you can ask what portion of the samples can be reconstructed. Is it all the training set? Is it part of it? So let's get back to the equations and see some property. If you look at this equation here, you remember this tells us whether the model is correctly classified, but in our case, because we kind of getting to the same solution as maximum margin, it tells us whether this xi is, it must be, this quantity must be larger than or equal than 1. If it's exactly 1, it means that this xi is situated on the margin. Otherwise, it's farther from the margin. This is very similar to SVM. Think of support vectors. This is very similar. But if you go to these equations, we see that this quantity that can be either equal or larger than 1. If it's not 1, it must be larger than 1. It must be further from the margin. If it's not on the margin, then lambda I is going to be 0. So let's go back here, and we see that for each sample that is further from the margin, well, margin is the samples that make this thing 1. So for each sample that is not on the margin, lambda is going to be 0. They are not going to participate in this set of equations. If I'm going to just take this to the other side, we see that the parameters of the model, of the trained model, are actually a weighted sum of something related to the samples multiplied by these lambdas. And from our simple analysis, we see that it is a weighted sum of only samples that lie on the margin. Again, very simple to SVM. In SVMs, you have the support vectors and they are the only ones that actually contribute to the parameters of the model. So get back to my point. If parameters are only dependent on samples from the margin, we cannot expect to reconstruct something that is outside of the margin. How do we measure this? So if for each sample from the training set, we look for the nearest neighbor of the reconstruction. Here it's in terms of SSIM, if you know this metric. So we're going to measure the similarity between samples from the training set to reconstructions using this structural similarity metric, which is a popular method to measure the similarity between images. This is going to tell us how well the reconstruction was. It is going to be closer to 1 if it's very similar, or lower if it's not similar. And that we are going to plot for each sample in the training set how well it was reconstructed compared to the output of the model. The output of the model tells us how far we are from the margin. If it is small, if it is closer to 0, it means that this sample lie on the margin. If it's further, it means that this sample is away from the margin. And what we show here, this is actually the margin for this model. We see that samples with good reconstruction, with high structural similarity to their reconstructions, are only samples that lie on the margin. We didn't manage to reconstruct anything that is far from the margin. And actually, there are also a lot of samples that are on the margin that we didn't manage to reconstruct. So we don't know exactly yet why. It is a quite hard question to ask. But you can use this sort of summarization of the reconstruction. And it is a nice way to look for each model. If we show this plot, you see how well we managed to reconstruct the samples. So you can see, we show that you can use models with different architectures. So it's going to be always from the dimension of the input to the latent dimensions stated here. And we show that for several architectures, we managed to reconstruct very well, also for different amount of training data. And I'm going to finish here. So let me summarize what I've just shown you. So we show that we can reconstruct large portion of actual training samples. We showed it for binary MLP classifiers. And we have no additional information on the training data. And the nice thing is that it is motivated from the theory of implicit bias of gradient descent. Now, there is a lot of things to do for the future. Of course, the most interesting thing is to see how well you can take this for realistic settings like convolutional networks, multi-class augmentations. You can check if you can do it beyond the theory. So there is a lot of assumptions on the theoretical version. It must be gradient descent, but would it work with stochastic gradient descent? Would it work with Adam? So we already have some preliminary results on this aspect. Interesting things would see if you can reconstruct stuff from other types of data like health or point clouds, etc., or if you can defend against reconstruction attacks. And so I want to finish by that. So thank you for the invitation, and I will stay here if you want me to say for more questions if you have. Oh, thank you all.
Yes, one question. If you do a different random initialization, do you get the same good outputs or some different outputs?
In the training or while in the reconstruction?
In the reconstruction.
So in the reconstruction, what we do, we actually, okay, for the optimization problem that I've shown you or showed you, we have this loss. You have to solve this optimization problem. You have to change access in order to minimize the loss. The way you do it is like you solve any optimization problem in your daily life. You do it with a gradient descent or Adam or whatever you need. For example, one hyperparameter would be the learning rate. We have to look for the learning rate in order to solve this. But there are actually 4 hyperparameters in our method. So one would be the learning rate, one would be the scale of the initialization. So I told you that they're going to sample it from some random Gaussian, but it has some scale that we don't know is going to be a hyperparameter. And there are 2 more. And the point is, so we don't know these hyperparameters that would get good reconstruction. So what we do, we just do grid search. We actually solve this optimization problem many times. So we solve this for, say, 1,000 initialization with specific set of hyperparameters. We run the optimization problem, we get some results. And then we do it like 100 times. We get 100,000 reconstructions at the end. So get back to your question, sorry.
The question was basically how robust is to the initialization. Will it converge to the same solution or to different solution every time?
So for each choice of hyperparameters, some of them would diverge. It will not converge at all if the learning rate is very high. For the others, maybe what you ask is, do we get the same reconstruction, the same reconstructed images all the time? So
the basic question is, can we get more reconstructions from the dataset by just doing different random initialization of the photos?
So you run it many times and you get different solutions, but most of the times you will get the same reconstructed images. there are some images from the training set that are, say, like stronger than others. For any time you run this you solve this optimization reconstruction problem, you will get them. Sometimes you'll get more or not. Maybe the question is, do we actually solve the optimization problem, our optimization problem? Do we actually manage to really solve it, or maybe you can solve it better? And I mean, I don't know. So in order to do it, you have to try all sorts of things. Empirically, you will get whatever I showed you. So if I get back to let's see, like the main results, for example, these ones, you will always get this one. Sometimes you'll get the one over here. Sometimes you get this one.
Don't see the presentation.
Oh, okay, sorry. Now you don't see it also, I guess. Okay, right? This is what you get, right? So when you solve it many times, so this is, I just tell you this like an empirically evidence from what I've seen from when trying to solve it. The first row is what you will get most of the time. So you solve this optimization problem with different hyperparameters, different turning rate, different scale of the initialization. You will see these popping up all the time. Sometimes you will get these ones, for example. This will not pop out in all the solutions. Sometimes you will get all of them. So what we do, we actually solve this many times, and we then have like 100,000 reconstructions, and we want to, then you have to kind of search in this 100,000 reconstructed images, search for the images from the training set. You can just look at it by yourself, but then, I mean, just to show that this is possible, for each sample from the training set, we look for its nearest neighbor in the reconstructed images, and that's what we got, the best ones.
Okay.
Does it?
Okay.
Yeah,
I basically got the answer.
Okay, great.
Can you show again the previous slide?
Which one? This
With
one?
The margins, yeah.
We don't see the entire
you don't see, yes, because I wanted to see some faces. Okay, okay.
So when you calculate phi here, it includes the true label. I mean,
so
support vectors can be, vectors on the margin or errors, basically. Is it by any chance related to the, like, are you reconstructing better the errors or things like that?
What do you mean by errors? So, I mean, let's go to SVMs. In SVMs, you have your data.
And let's say you have a misclassification by your model, like an error of the model. So you classify the opposite class.
Okay. So important assumption in SVMs, in hard SVM, is that your data would be linearly separable. Okay. So this is hard SVM. If it's not the case, then you can either go to like soft SVMs. So let's leave it at that. What is actually more related to our work is to think of it as the kernel SVM. So you will look for some kernel that after feeding your inputs through this kernel, you will get to some space, that in this space, the data would be linearly separable. And then you just solve hard SVM with kernels. Why this is similar to our case? Because you can look at the MLPs, you can look at all the layers up to the last layer as kind of the kernel, and then you just do hard SVM on the last point. So also,
if you use real data, so it's still not promised to you that this is really a hard SVM.
Right. Okay. So one of the assumptions in the theory that I've showed you is that at some point we will have zero training error. So at some point during the training, all the data sets will be correctly classified. So this is actually easy to get. So yeah, it's true, not always this is the case, but this is the case in our examples. And if your setup is relatively like simple, 1,000, 10,000 images, I think from my experience, it is normally the case. I mean, when you train over parameterized model, you will get zero training error, right? So you get also, but it will get to this solution that also generalizes very well. So you don't lose by getting zero training error, because then the theorem says that it will also generalize better. But basically, what I showed here, after you train your model, you can just look at the confidence of the model on each sample, and the lowest confidence samples are the ones that are on the margin. So this is the x-axis. This is just the output of the model, which is in binary classification, just it's the confidence. Okay.
Mm-hmm.
Any more questions? Okay.
Okay. Thanks a lot.
Niv.
Thank you for the invitation.